So the probability of an event is always a number between 0 and 1. Sometimes, like when we set them up, a lot of times we'll set them up as fractions, but they also can be decimals. But it's somewhere between 0 and 1. A probability of 1 means the event is guaranteed to happen because it's like 100%. And a probability of 0 means an event will never happen. Like there's a 0% chance that that would happen, that sort of thing. Okay, so then we have, I think I'm going to skip over some of this stuff. We've got random experiment. It's an act. It's just something we don't know what's going to happen in the end. The outcome, that's your possible result. We don't need to take time to read. The event is the whatever's happening itself, and then your sample space is all of your possible outcomes. That stuff's kind of not as relevant as going through some of these actual practice questions. So the probability of an event, I'm not sure how important the notation is, but we'll just put it on there. Probability of an event is determined by the number of successes or the number of things that satisfy whatever the situation is, like the number of red chips in the bag or whatever, over the number of possibilities. So if I gave you like a little bag of M&Ms and you want to know, what's the probability of you drawing a red M&M? You know, the number of reds over the number of total M&Ms, whatever. So a lot of probability stuff deals with a standard deck of cards, which it always amazes me how many people don't know a whole lot about decks of cards, which it's fine but it is something that you're kind of expected to understand for questions like this. So even if it doesn't say 52, we should know there's 52 cards. So let's talk about a couple of other things with cards here. We'll just kind of put this at the bottom. You have a little bit of room at the bottom, right? So if I have 52 cards, and do you know what the suits are in a deck of cards? What that means? How many suits are there? 4, okay? 4 suits. And doesn't even matter if you know what they're called, but there's 4 of them. How many colors? 2 colors, yeah. Because it's either red or black, right? You got 2 that are black, 2 that are red. So 52 cards, 4 suits, which means each suit has how many cards? $52 divided by 4. What's 52 divided by 2? 26. Think about having 52 cents. You've got 2 quarters and 2 pennies, right? So 26, and then half of 26 is 13. Okay. So there are 13 cards, 13 of each suit, I guess is what we can write down, so we can know how to think through this stuff. And then if there's 2 colors, there's 26 of each one of those, right? How many face cards are in each suit? There's the Jack, Queen, and King, right? So there's 3 face cards, 12 total. Joker doesn't count. Joker's not part of the 52. Thank you for saying that. Joker's like the extra, okay? So doesn't really get put into the 52. And usually not part of the, now that you say that, I don't know that I've ever seen a Joker be a part of any probability question I've ever seen. Not that it couldn't be, but I never really thought about that. So we've got 52 cards, 2 colors, 4 suits, 13 of each suit, 3 face cards, cards, and then that's really 12 total, right? So there's 12 total face cards, but 3 of each suit. Okay, does all that make sense? We all know that, right? Should have maybe brought a big deck of cards or something. Okay, so that means not only there's 3 face cards for 4 total, but how many 7s are in the deck? 4, right? Because there's 4 suits, so there's a 1 7 in each suit, right? Okay. So when we're looking for a standard deck and a standard deck of 52 cards, determine the probability of drawing the following. So the probability of drawing a 5. How many 5s are there? 4. And that's out of a total of what? 52. Okay, so that's fairly simple, right? And so then when you reduce all that, that gives you that 1 out of 13 chance of drawing that. And remember also, I'm going to kind of give you the final answers on this. You do, I double checked because when it came out of my mouth the other day, I was like, I think that's true. You do have access to the Desmos calculator for the entire test. So any division, multiplication, any of that stuff you have to do, the Desmos calculator is there. Also, now that I said that, I tried in Canvas earlier. I can't transfer something from one class to the other. So I haven't put it in yours yet, but I will. Just so that you can actually look at it. Not that this will work now, but the, crap, where is it? Okay, here we go. This is what the Desmos calculator will look like. It looks just like if you went to desmos.com, I know. But there are multiple versions of the Desmos calculator. How the SAT version, PSAT version is different than just desmos.com, have no idea. Maybe it's not different at all. But if you go and so I searched up the different Desmos testing calculators, and there's a bazillion of them for different states, different tests. But I will put the link to this in Canvas, like if you're doing it, practicing for the SAT and you want to see, try to do something and see if it actually works in this one, then I'll put that in there. And I'll also put in there the reference materials that I found, finally. Okay. So then the probability of a red ace. How many red aces are there? 2. So that's just 2 out of 52, right? And then you can either reduce the fraction or get the decimal. That would be 1 out of 26. Probability of a number greater than 5. Okay, so 2 things here. First of all, it says a number. Jack, queen, and king, are they numbers? No. Is the ace a number? No. It can be counted as a 1 or an 11, depending on what game you're playing or whatever, but it's not an actual number. So the numbers greater than 5, in a situation like this, I would actually list them out so I didn't do anything weird. 6, 7, 8, 9, 10. Is there an 11 card? No. I have 1, 2, 3, 4, 5 numbers greater than 5. I'm not including 5 because it says greater. So am I just putting 5 out of 52? Is that what I would write? Multiply it by what? 4, because I got 4 suits. So 4 times 5 is 20. That would be my 20 out of 52. Okay. Everybody okay with that? This is like very basic probability. It's more likely that you're going to have a little bit more advanced probability, but we'll get to that in just a second. Probability of drawing a red or black card. How many red cards are there? Okay, no, you're fine. How many red cards are there? 26, right? Oh, I was wondering what you forgot. I was like, I didn't think you forgot your phone. There's 26. How many black cards are there? 26. Are there any cards that aren't red or black? No. So this is just 52 out of 52, which gives you what? Oh, that's a 51. 1. Because it's a 100% chance. If you draw a card, it's going to be a red or a black card, unless you have some weird card deck. Like I have some that are red and green because they're Christmas, but that doesn't count. Probability of drawing an 11. How many 11s are there? None. So that's 0 out of 52, which is 0. Probability of drawing a 7 or an 8. I'm just drawing one card. How many 7s are there? 4. How many 8s are there? 4. So there are 8 cards that would make me happy, right? So that's just 8 out of 52. All right, everybody okay with that? Again, that's just like your super basic refresh about that stuff. All right, so the next part here is more like what the probability that you'll really be asked for. When finding the probability of 2 or more events, you find the probability of each event, and I think this is where the confusion about what to do and what you remember to do correctly. You probably find the probability of each event and multiply them. Okay. Then there's probabilities with and without replacement. The actual word replacement is probably not going to be in the question itself stated like that, but we'll talk about what that means. So if you were finding a probability without replacement, That means that I draw a red M&M, I eat it, and then I draw another red M&M, right? So I have less to draw from this time. The number of items in your sample space will decrease with each new event because you're taking them out and not putting them back to draw again. Then we also have independent and dependent events. So a dependent event would be I draw a red M&M, I eat it, and then I'm going to draw another red M&M and eat it. What's the probability of doing that? Well, the second draw depends on what I drew the first time, right? It's going to change everything. An independent event, if I had more than one, would be like if I'm going to flip a coin and roll a die. They have absolutely nothing to do with each other. Okay? So if I have independent events, the occurrence of one event does not affect the probability of the other. That's the actual definition of that. Dependent events, the occurrence of one event does affect the probability of the other. Then we look at, is there replacement? Okay, so if they do not, if it does, oh, I'm sorry, that's totally separate. Is there replacement? If it is yes, we look at that, and no, here's what happens here. The probability of A and B happening. Probability of me getting a red M&M and then a blue M&M. That means this is the probability of A happening times the probability of B happening. Okay? If I have 10 M&Ms, probability of drawing a red, there's 2 out of 10 for that. And then probability of drawing a green, 2 out of 10 for that, whatever it is. And then if there's not replacement, then it's the probability of A times the probability of B after A happens. Okay. What we're looking at there. Okay, so we're just going to look at, are these independent or dependent? So Ben rolls a 3 on a number cube. The other thing is they probably, I don't know, in the SAT they might call them dice. In like high school textbooks and stuff, they usually say number cube. So it's not like a gambling thing. It's very odd how things work. But a number cube is just a die. That's all it is. So he rolls a 3 on a number cube. Then he rolls a 4. Did his 4 have anything to do with what he rolled the first time? No. So these are totally independent events. Okay. Mary chooses a prize out of a bag and keeps it. Then Grace chooses a prize. Does what Grace gets depend on what Mary got? Yeah, so these are dependent events. Greg picks a red crayon out of a box, uses it, then puts it back. Then Joe picks a red crayon. Independent or dependent? Independent, because there was replacement there. Okay. All right. So when we have a 6-sided die is rolled and a coin is flipped, find the following. Probability of rolling an even number and flipping heads, right? So if I roll a number cube or a die, how many even numbers are there? 3. Because it says 6-sided. If you don't know that there's 6 sides, you should know, because it just may say like a die, and then we need another 6 sides. So the numbers are 1 through 6, and so there's 3 even numbers. So an even number would be 3 out of 6. And then heads, that would be 1 out of 2, right? You find the 2 different probabilities and you multiply them. That's all that's happening. And then that's going to give you 3 out of 12, which you got a 1/4 of a chance of that actually happening. Okay? Everybody okay with that? All right. Probability of 6 and tails. How many 6s are there? 1. 1 out of 6. Times, what's the probability of flipping tails? 1 out of 2. So you got a 1 out of 12 chance. That's how you do that compound probability stuff. Okay. Which is this at least part of what you were asking for kind of a refresher on, right? Okay, just making sure I was on the right track here. All right. Prime number in heads. All right. How many prime numbers are there on the die? And if you need 1, 2, 3, 4, 5, 6. Do we know what a prime number is? Yeah. So 5 and 3 and 2 are prime numbers, right? 1 is actually not a prime number, and that's a little tricky. To me, this kind of question is not just testing probability, but if you really understand that 1's not a prime number, but we won't go there. So there's 3 prime numbers. So it's 3 out of 6 times 1 out of 2. And then you get that 1/4 again. A number less than 5. How many numbers less than 5 are there? 4. So that's 4 out of 6. And then the coin's easy because it's just going to 1 out of 2 each time. So that gives me a 4 out of 12 chance. And you know, y'all probably are way better at Desmos than I am because you at least used it in Algebra 1, and I've never really used it that much or taught with it. Will it reduce fractions for you, or does it just change everything to a decimal? Do we even know? It reduces fractions for you? Okay. So either way, that's 1/3. Something I need to play with. Just thought about that. All right. A number greater than 1 and heads. How many numbers are greater than 1? 5. 5 out of 6 times 1 out of 2. 5 out of 12. All right. So let's look at these. Using a standard deck of 52 cards, you draw 2 cards and do not replace the first card. Okay, here's your non-replacement. These are definitely dependent events. So the probability of drawing an 8, then an ace. How many 8s are there? 4, right? So I do 4 out of 52. And then an ace. How many aces are there? 4 aces, right? Is this going to be 4 out of 52? What is this going to be? 4 out of what? 51, because we did not replace the first card. Okay, that means that this is 4 times 51. So you have to subtract it because you kept it out. So don't forget about those things. Then when you multiply it all, like I said, you'll have access to the calculator and everything. It's 4 over 663. And I would imagine that the reduced number is the answer. I doubt that they would give you a non-reduced number. All right, probability of drawing a face cards. How many face cards are there? 12. Okay, so that's a 12 out of what? 52. Okay. Yes. How is what 4? Oh, we do multiply, but when this is reduced, multiplied and reduced. I'm sorry. I probably shouldn't have skipped that. When you actually multiply that, it ends up being 16 over, actually I don't even have that because the way I did it, I reduced stuff. I don't know what it is. 16 over whatever 52 times 51 is. Sorry about that. I just gave you the final answer. Because when I did this is the last time I did the geometry part of it. I wasn't even letting them use calculators on this, so we were reducing and practicing multiplying, and yeah. All right. And then a red 7. How many red 7s are there? 2, because there's 4 7s, 2 of them are red. So it's going to be times 2 over what? 51 again. And then the final reduced answer, whatever it is 2 over 221. Okay, probability of drawing an 11 and then an ace. So I know I have 2 things here, right? And since I'm going to keep that, the denominator here is 52, then this one's 51. How many 11s are there? There's 0. There are 0 11s, so it doesn't even matter what the next, even though this would be 4, that doesn't even matter, right? Your answer is just going to be 0 there. Okay. So probability questions, they like to use the dice, they like to use coins, they like to use cards, they also like to use marbles in a bag or something like that. And so we have a bag of marbles contains 3 yellow, 2 blue, 7 green, and 5 red marbles. Without looking at the color, you reach in the bag and select 1 or more depending on what's going on. So the probability of a red marble. How many red marbles are there? 5. out of a total of how many? Is it 17? Do y'all agree with that? It's 17. If they don't tell you, you have to add them up. Make sure you actually add them up correctly. And then now we know it's 17, like for the total for everything we're going to use. You only have to add it up once. And remember, the probability could be a fraction, it could be a decimal, but you have a calculator, you could divide it out and get the decimal if you wanted to. So probability of a green marble, then a yellow marble without replacement. So how many green marbles are there? 7 out of a total of 17. And then yellow, how many yellows? 3 out of how many? 16. Good, because it's without replacement. And then when you multiply, you get 21 over 272. So the without replacement, that makes this dependent. That's what changes the denominator. 25, we've got with replacement, that means it's independent. That tells you that your denominators are going to be the same, the whole thing, right? How many greens are there? 7. And how many yellows? 3. So then we get 21 out of 289. I'm going quickly. Am I going too fast? Or this is just kind of the refresher you needed? We're good? Okay. Green marble, then green marble with replacement. Okay? So how many greens are there? 7 out of 17 times with replacement would also be 7 out of 17. Because, again, this is independent, and this would be 49 over 289. These didn't reduce any, just straight up multiplied. So then, same thing, green marble, then green marble, but this says without replacement. That is dependent. So 7 green marbles out of a total of 17. What do you think the numerator is on the next one? There's 7 green marbles total, right? The probability of drawing a green marble, keeping it, and then drawing another one, how many, if I draw one and I keep it, how many are left in the bag? Greens. 6 out of a total of 16. Okay? So I'm not using the 7 again there. I multiply, this does reduce a little bit, and it gives me 21 over 136. Okay? What questions do you have? Does that help on the probability stuff a little bit? Okay, so there's another kind of topic that goes along with this basic probability, and I just have the first page is all we need here. It's the counting principle, and it does also say factorial at the top. We're not going to go there. I didn't even put that on here. It's just part of the title. But tree diagrams and then counting principles, the kinds of questions where they might say, okay, you go into your closet and you have 3 pair of pants, 2 shirts, a belt, 5 pair of shoes, whatever. Like, how many different outfits can you make? Of course, we're not thinking about what fashion would actually look like at all. Those kinds of questions. And this is a very simple, basic idea, but I think it does throw people off. And you could stand just a little bit of refresher on this as well. And there's a couple different ways to do this. You can draw it out, okay? But sometimes the numbers are really big, you don't want to. But we are going to at least draw one out so you know how it works, and then we'll talk about how you don't necessarily have to. So you can do what's called a tree diagram. They are used to display possible outcomes. And it probably helps if you're more visual or if you forget how to do the actual math. And count possible outcomes. That's why it's called part of the counting principle. Would y'all like to get up here and teach this? Then be quiet. Okay. The school cafeteria sells sandwiches for which you can choose one item from each of the following categories. These kind of questions also assume that you have to. You can't say, I don't want ketchup or mustard. That's like not an option. You're going to choose one, is how these are usually done. So the school cafeteria, this is what you get to choose. You've got 2 breads, either white or wheat, 2 meats, turkey or ham, and 2 condiments, ketchup or mustard, which sound like terrible sandwiches, but this is what we have. So what we can do is this. Okay, I've got two breads. Like, my bread's already written out. So, okay, if I choose white bread, then the next thing I choose is I choose either turkey or ham. So here's turkey, here's ham. And then after I choose turkey or ham, I have to choose, I can get turkey and I can either get ketchup, I'll just put a K, or mustard. And if I choose ham, I could choose ketchup or mustard. And it never really occurred to me how, like, white bread with ham and ketchup, I don't know, maybe that's somebody's jam, but that just does not sound good. Or I could choose wheat bread. And if I chose wheat bread, then I could choose turkey or ham. And then from there, I choose either ketchup or mustard. And here, ketchup or mustard. So how many different sandwiches could you actually have? And you don't get to choose like turkey and ham and pay extra or anything like that. So what we have here are this end of these trees, kind of like when we looked at the, when we were simplifying a square root, you made little trees. Those are the ends. So once you do that, you can add them all up and you get 8 possible outcomes. That's what's happening there. That's your actual possible outcomes, and there's a total of 8 different sandwiches you could make. Now think about if you went to Subway and you had to do this diagram, it would look insane because you could choose more than one and it would just be crazy. So we definitely don't want to always have to do things this way, but if it's very basic, you can if that makes the most sense to you. But then there's the counting principle where we're going to put a little bit of math behind it, and once you get it, it's not that big of a deal at all. So if there are n ways of making one choice and m ways of making a second choice. You have 2 pair of pants and 3 shirts. So I have 2 ways of picking pants and I have 3 choices to make for shirts. So then there are n times m ways of making the first choice followed by the second choice. And again, this is generally used when the diagram is too large, or even if it's not. We could have done that up here. Here's the way to me, it always makes the most sense, is to say, all right, I'm going to have to choose a bread, I'm going to have to choose a meat, and I'm going to have to choose a condiment, right? Or however, so I have 2 of these I get to choose from, 2 of these to choose from, and 2 of these to choose from. When I multiply 2 times 2 times 2, I get 8, right? That's all you're doing. It is that simple. So if you have 2 pair of pants and 3 shirts, you have 6 different combinations you could make. That's the way that works. So here's this. You have 7 shirts. So I have shirts, pants, belts, and shoes. And again, nobody cares if they actually look good together. We're just making combinations. So I have 1, 2, 3, 4. I'm going to make 4 blanks. And even when I do this, I usually make blanks so I don't forget to put everything in there. Then I have 7 shirts, 3 pair of pants, 2 belts, 3 pair of shoes. And then I just multiply all those together. And when I multiply all those together, that is 126 different outfits that you have, but you probably still feel like you have nothing to wear, right? It's just the way it is. Everybody good on that? Because again, this is pretty basic and it's simple, but it's also easy to overthink if you're not really sure where to go with it. Now think about your computer passwords. 3 letters followed by 3 digits, or 3 numbers, which I don't even think, if you make a new password for anything, yes ma'am. Yeah. Absolutely, that's all it is. However, yes. So up here, we made this tree, right? Because if that makes sense to you, you can do that. But all I did was, I have bread, meat, and then condiment. Yeah, you just put in however many choices you have for each, and you just multiply the numbers, and you're done. Get the exact same answer. So why you would want to do this, I don't really know, but but it's a possibility. Or it could be written out for you. Sometimes they give you a tree, and then you're trying to figure something out. But I'm sure there's good reasons for it. But yeah, we're just multiplying. That's it. Because think about what this tree would look like. That'd be crazy, right? I'd have to have 7 things to start off with, and then from there I branch off to 3s. Like the tree would get really big. Good question. Anything else? All right. So now we're choosing a computer password. If you create something right now and you go to choose a password, you probably aren't even allowed to have anything less than 8 digits, right? And you have to have a capital or a lowercase and a special character and all these different things. So this is like a very basic password. It says how many passwords are possible if the letters must be uppercase? All right. Well, I have 1, 2, 3 letters and 1, 2, 3 digits. Okay. So how many possible letters can I choose from? If this is the English alphabet, I should say. How many letters are in the alphabet? 26. Good. Nobody had to count on their fingers, and we got it. 26. Now, it doesn't say you can't repeat them, so you absolutely can repeat them. If it said you cannot repeat the letters, it said I cannot repeat them, what number would I put here? 25. But it doesn't say that, so this could be 26 again. And then 26 again. There are my 3 different letters, or 3 of the same letters, doesn't matter. Then my 3 digits. If I have a 1-digit number, how many options do I have to put in there? 10, because what did you include? 0. So you actually have 10 because 0 counts as a digit. Okay. Then 10 times 10. Okay, so just this, think about how simple and basic this password is compared to what you are required to do anymore. And anybody want to take a guess at what that number would be? Okay, let's see. This number is 17,576,000 options. You're pretty close. And sometimes things like this, because we'll talk about another, which I don't know what the answer is off the top of my head. We'll have to actually multiply it out, but I'll give you one other example when we're done, which always seems wacky to me. How many passwords are possible if no letter or digit can be repeated and the letters have to be lowercase? Right? Now just think about if they could be uppercase or lowercase, I'd actually have 52 to choose from, right? Because it would basically double my alphabet. So now I can't repeat anything. Okay, so I have 6 spots again. So that means I would start with 26, then go to what? 25, then go to what? 24, all right? Then this would be 10, then what? 9, then 8. Multiply all those together, and you still get 11,232,000 different possibilities. Now, one of the things that, and you can do this on the back if you wanted to write it down, you don't necessarily have to write it down. One of the things this talks about is factorial, which that has to do with combinations and permutations, and that's something that I guess we could pop up as some of those really harder questions. But let's think about you're a baseball coach, right? And so how many people, can anybody tell me how many people are in a batting lineup? Anybody know? Jacob, you play baseball? No? You're looking at Jacob. 9, how many? There's 9. There's 9. There's 9 players in a batting lineup, right? And there's 9 players on the field. And obviously, the coaches are going to, who your leadoff batters and stuff has to do with ability. But let's say we got a little league team and they're all it's like herding cats. It really doesn't matter. So order, whatever. Then let's think about how many options they have. They would have 9 spots to fill, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. They would have 9 spots to fill. So when we have our 9 people we're choosing from, when we go to choose the leadoff batter, we got 9 options. Then we have 8 options, right? Then we have 7, 6, 5, 4, 3, 2, 1. Okay. And if you multiply all those together, because we're doing 9 times 8 all the way down to 1, that is the same thing as 9 factorial. It's not an excited 9. That does mean factorial is something you should have at least been introduced to. But I'm just want you to think about, like, how many different options do you think a coach has to make this lineup? Just come up with whatever number you think it is in your brain. You don't even have to tell me. But because anytime we do something like this and then we talk about it, it just seems insane to me what the number actually is. And then, of course, I hit the wrong number, and oh my gosh. I don't know where the factorial symbol is, so I'm actually multiplying this out. That is 362,880. That's how many different batting lineups you could have with 9 people. Doesn't that just seem wrong? So sometimes combinations and probability, it just seems wrong, but it is correct. And again, passwords, we were up in the 17 million options, and that was only 6 digits with very basic stuff. So there's crazy different numbers for the counting, okay? What questions do you have? We all kind of good on that? One thing I do want to say about the SAT